Welcome dear students to part B of lecture 2 on structural dynamics, which covers free vibration of single degree of freedom systems. So in the last class, part A of this second lecture, we have learned how to formulate the equation of motion of a single degree freedom system. We have studied the various kinds of vibrations, namely free and forced vibrations, and we have learned that both free and forced vibration can be either damped or undamped, and we had analyzed the physical mechanism which drives the undamped free vibration of a single degree freedom system, and we saw that the conservation of energy is the physical reasoning or physical reason behind carrying out any undamped free vibration. In addition to that, we have also learned in the last class few terms related to free vibration, namely the natural frequency of vibration, and we had seen that the natural frequency is given by root over k by m and since k and m are system property of the dynamic system, single degree freedom system, that's why we call this as natural frequency that we have learned. And we should also highlight the fact that the unit of this natural frequency omega is measured in terms of angle in radian per second. So unit is radian per second. It is in short written as radian per second, and the time period of motion, time period of free vibration, is the time required to complete one cycle of motion. And since in one cycle of motion there are twice pi radian, therefore we can write that obviously omega times the time period will be my twice pi, right? And hence omega is also given by twice pi by t. So t can be obtained as twice pi by omega, and hence we can see that t is obtained as this, and this can be simplified to twice pi root over m by k. This equation also we had already seen yesterday, remember? Now we have another term called frequency of vibration, okay, and this frequency of vibration is measured in cycles per second, and it is defined as the inverse of the time period, okay? That means how many cycles takes place per 1 second is called frequency. It is denoted by f, and this is my equation. Obviously it is 1 upon t, so it will be given by 1 by twice pi root over k by m, okay? This is measured in cycles per second, or it is also called hertz. So we write as in short c by s or cps, cycle per second, or hertz, okay? And we also knew that in SDF system the calculation of natural frequency or time period is an essential part of the analysis. Okay. So with this background, now let us go for easy solution of equation of motion of undamped free vibration. We have seen the physical approach, where from the conservation of energy principle we have derived the solution of equation of motion, and thereby we have got the natural frequency expression for natural frequency. Now the same equation can be solved just like a ordinary differential equation, second order differential equation. So my equation of motion is this. We already know that my equation of motion for undamped free vibration of single equilibrium system is this: mx double dot plus kx equal to 0. I can replace x by any letter, for example u or y or z. So in dynamics, please don't try to remember the equation, rather you should remember the structure of the equation. If the acceleration term is there and the displacement term is there, you know that it is an undamped vibration. If the right hand side is 0, then you know that it is a free vibration. And if acceleration, velocity and displacement, all these three terms are there, then it will be a damped vibration, as we have already seen. So it doesn't depend on the we need not be concerned about the notation used for the deformation or mass or stiffness, etc. If we understand the structure of an equation, we immediately come to know what does it physically mean. Okay. Now coming back to this equation, this is a second order differential equation with constant terms, and it is a homogeneous equation because the right hand side is 0. So we can use the method of auxiliary equation to solve this differential equation. So what we have done is we have divided both the terms by m, so that I get k by m here, and instead of k by m I can just put as omega square. We are writing square because it is a second order equation. That is the method of solving any differential equation, you know. So therefore from this I can find out the corresponding characteristic equation as this, right? This is my corresponding characteristic equation, where it is solved for lambda. Lambda is my characteristic root, and therefore since this is a second order equation, second order term, I will have second power of lambda. So lambda square plus omega square is 0, and therefore I get from here what I get. I get lambda square is minus omega square, and therefore my lambda is plus minus root over minus omega square, and therefore I know that square root of minus 1 is I, imaginary number, therefore I get lambda equal to plus minus I omega. Alright, and therefore once I have these characteristic roots, I can write down the solution of my equation as in terms of exponential functions. Okay, so this is basically x is a1 into e to the power plus I omega t, the first root lambda, plus a2 e to the power minus I omega t, right? And therefore now I know that from Euler equation e to the power I omega t is plus minus I omega t is cos omega t plus minus I sin omega t, and therefore I will write this value in this equation. So from here what I'll get? I'll get let me make some space, it is not working. I don't know why. I think I'll have to add one layer. No, I'm unable to add space somehow. Anyway, let me write it here itself. So I get A1 into cos omega t plus I sin omega t plus A2 cos omega t minus I sin omega t, right? And if I simplify, then if I take cosine terms common, then I will get A1 plus A2 times cos omega t and I A1 minus A2 sin omega t, and those things I can replace by another constant, say C1 and C2. Therefore finally I can write x in terms of cosine and sine functions, C1 cos omega t and C2 sin omega t. And these values of C1 and C2 can be obtained from the initial conditions of the system. Okay, so now let us evaluate the integration constants. If I evaluate the integration constant, then I have this. Therefore if I take the initial conditions as x at time t equal to 0 as x naught, and x dot at time t equal to 0 is x dot naught, then what I will get from here at time t equal to 0, let me write it here, x naught will be my C1, right? When I put t equal to 0, this term will remain, so C1. And from here, if I differentiate, then what I will get, we have already seen this thing yesterday. X dot is minus C1 omega sin omega t plus C2 omega cos omega t, and therefore if I put at time t equal to 0 the value of velocity, then I will get at time t equal to 0 x dot is x dot naught, and this will be given by C2 times omega, and hence my C2 is x dot naught by omega, and therefore my final solution will be this one, right? My final solution is this, x equal to x naught cos omega t plus x dot naught by omega sin omega t. So therefore I can express my displacement in terms of two terms, one cosine term and one sine term. Okay, and this natural frequency is the argument of this sine and cosine functions. All right, now any two sum of harmonic functions, you know that we can express them as either sine or cosine terms, and therefore if I want to express it as sine term, then I would like to have sine A cos B plus cos A sine B formula, and therefore what I will do is I will use x naught as r sine phi and x dot naught by omega as r cosine phi. In that case I will get what? From here I will get this will give me r naught cos omega t sine phi plus r naught sine omega t cos phi. So I get sine A cos B cos A sine B term, so I will get finally sine A plus B term. Okay, therefore this will be my I am using r naught, in the note it is r, so let me remove this naught. So I have r sine omega t plus phi, where phi is what? R is what? R, I can just square and add these two terms, then I will get r square terms times sine square phi plus cos square phi, and therefore r will be given by this quantity. R will be given by this quantity, and tan phi will be given by x naught divided by x dot naught by omega, right? So tan phi from here, from these two equations, I can write tan phi as sine phi by cos phi. Therefore I have x naught divided by x dot naught by omega, so this omega will go up, and hence I will have phi equal to tan inverse of this quantity. Alright, so that I can express this sum of sine and cosine terms in terms of a sine function. This sine function has a new amplitude r, peak value. Amplitude means peak value of the harmonic quantity, and it has a phase difference with the original harmonic quantity, and this phase difference is given by this quantity, right? So this is how we can express it as either sine term or cosine term. For example, if you want to have a cosine term, then what will happen? I will write cos A cos B plus sine A sine B formula, so that I can write cos A minus B formula. Okay, therefore x naught will be r cos phi and x dot naught by omega will be r sine phi, and in that case my amplitude will remain same, but the phase difference will be negative of this by this, is not it? Because you see, let me do it here. Let me insert a page. Let me write it here, or let me write it here. I have x is x naught cos omega t plus x dot naught by omega sine omega t. Now I want to express it as a cosine term. Therefore what I will do is I will write x naught as, so let, I'm sorry for my bad handwriting, x naught is r naught cos phi and x dot naught by omega is, say, r naught sin phi. So therefore my original equation will become r naught times cos omega t cos phi plus sin omega t sin phi, right? And we know that cos A cos B plus sin A sin B is cos A minus B, so I'll write r naught cos omega t minus phi, where my phi is how much? Phi is this divided by this now, just inverse of the RD of phi. So phi is tan inverse of x dot naught by omega divided by x naught, so it will be x dot naught by omega x naught, right? So this phi is just opposite of earlier phi. You can see, let's see here, my phi was this, whereas now my phi is just inverse, and this has a negative sign. Now this phi actually indicates that there is a lag of time between the original quantity, which was having a frequency of omega, and the new quantity. For example, if, say, if I draw the original quantity as a harmonic quantity like this, okay, this is my t. Now this will have peak at a different time, not at the same time. So this time lead or time lag is given by this phi value, is not it? Because when t is 0, the t for the second quantity will be, the quantity for omega t will be phi, omega times t will be phi, right? And that's why this is called phase lead or phase difference, because here the resultant is leading the original term. Therefore, because phi is positive, I call it phase lead, and if phi is negative, then I will call it phase lag. Alright, so in this case, this is my phase lag. This is my phase lag. Alright, so this is how we get the sine or cosine term both. I can express any harmonic quantity as a single harmonic quantity with some phase lead or phase lag with the original harmonic quantity. And therefore now I can express a harmonic quantity in terms of a vector. Okay, in terms of a vector. To understand this, let me write down my original solution. What was my original solution? We had got x was my x naught cos omega t plus x dot naught by omega sine omega t, right? Now you know that phase difference between cosine and sine term is pi by 2. Therefore, instead of cos omega t, I can write sine omega t plus pi by 2. And this term will remain same. In that case, now if I express this second term as a vector, I can assume that this length is x dot naught by omega t, x dot naught by omega. Okay, this length, I'm sorry, I'm very sorry. Let me try an arrow. Say this length is my x dot naught by omega. In that case, this quantity x dot naught by omega into sine omega t can be taken to be the y component of this vector, which is rotating with a circular speed of omega, and it has rotated over a time t. So this quantity, this vertical projection, is giving me the second term of this equation. Second term of this equation, right? Similarly, the first term of this equation is a sine term with a 90-degree phase difference with the original vector. Therefore, I can take this vector, which is having a 90-degree lead with the original vector, and therefore the first term of the equation is this vector. It has a length of how much? It has a length of x naught, because it is x naught sine omega t plus pi by 2, or x naught cosine omega t. So the resultant is given by this vector. Okay, this vector plus this vector, the resultant is this. And if you see this geometry, we can easily find out that this resultant is root over d square plus d square, which we have already seen in the last derivation. D square plus d square, length square of the two vectors, root over, this gives me the length of the resultant vector, and it is making an angle of phi with the original vector, where phi is tan inverse of this by this now, right? So these equations simply mean that the harmonic quantities I can express as rotating vectors, and the speed of the rotating vector is same as the natural frequency of the system, that is omega. Clear? So the speed of rotation is omega. Okay, you remember the video we saw in the last class where we have seen the I had shown you this video yesterday. Let me show it to you once again. I'm sorry. You remember that there was a mass moving to and fro, vertically up and down, and there was another point moving in a circular motion. The same thing is expressed by these vectors actually. Okay, and this quantity, length of these vectors, are called amplitude of the harmonic quantity, amplitude of the relevant harmonic quantity. All right, so that's how we can represent any simple harmonic quantity with a rotational vector. Okay, and therefore now if I have a deformation, say deformation expressed by sine term or even cosine term, say I have a deformation, say x equal to x naught cos omega t or sine omega t. Let me take as sine term to correspond to this diagram. Let me take it as a sine term. In that case, what is x dot? X dot is x naught omega cos omega t, which is nothing but x naught omega sine omega t plus pi by 2. Right? And if I further differentiate it to find the acceleration, what will I'll get? I'll get from here, it will be minus x naught omega square sine omega t. So this will be basically x naught omega square sine omega t plus pi, right? Therefore, if the displacement is this vector, then velocity vector will be just at 90 degree to the displacement vector because of this pi by 2 phase difference, okay, phase lead, and the acceleration vector will be at a phase lead of angle pi, so it will be just 180 degree ahead of the original displacement vector, and their amplitudes will be different. The first vector is having this much amplitude, so this is the radius. For the second, this is my radius, omega into x naught, so length of this vector OB is omega a, and length of this vector OC is omega square a. We have already seen. If this is a, if this is x naught, then omega square x naught, right? So like this, we can represent harmonic quantities in terms of rotating vectors, okay? And this type of diagrams are called phase plane diagram. This is basically a phase plane diagram. This is a very important tool in dynamic analysis of systems such as say mechanical system like engine. Say you have the to and fro motion of the piston, and that will be converted into rotational motion by the crankshaft, okay, and therefore there will be some phase difference between the motion of the crankshaft and the piston. So all those things can be expressed in terms of these phase plane diagrams. So your mechanical friends will be heavily using phase plane diagram in dynamic analysis of machinery, okay, and we civil engineers can also fruitfully use such vectorial representation of simple harmonic quantities. For example, suppose if I have a single degree freedom system, undamped single degree freedom system, what are my terms involved? I have m u double dot plus ku equal to 0, right? And therefore I have acceleration vector and displacement vector, and we have already seen that acceleration vector and displacement vectors are in 180 degree out of phase. All right, therefore if my motion vector is this, then the acceleration vector is in the opposite direction. It is not opposite direction actually, but it is 180 degree out of phase. Remember, these angles here means phase difference only, because it is a phase plane diagram. Now if now my motion vector is in this direction, then restoring force will be in the opposite direction, and the inertia force will be opposing this acceleration vector, so it will be in this direction. So I have m omega square a equal to k times a, and therefore for equilibrium this restoring force must be equal to this inertia force, and therefore I get m omega square a is equal to k times a from force equilibrium, and therefore omega square will be simply k by m, right? I have k by m. So same expression I get much more easily for the natural frequency by representing the forces in terms of rotating vectors, okay? So that's how we can use the rotating vectors to analyze dynamic motion of a single degree freedom system. All right. So next, let us see the analysis of damped free vibration. And you are already familiar with the equation of motion of a single degree freedom system subjected to damped free vibration. As you see, we have the damping term here, and the right hand side is 0 because it is free vibration. So this is again a second order differential equation, homogeneous differential equation with constant coefficients, and it has both second and first order terms, and therefore my auxiliary equation will be given by this m lambda square plus c lambda plus k equal to 0, and this being a quadratic equation, it can be easily solved. So lambda will be given by this expression. So I have two values of lambda, lambda 1 and lambda 2, which are given by this plus and minus sign, right? Now let us use c by twice m equal to n. This is a shorthand, you can say. So instead of writing a fraction, I am writing a simple letter. So if I call c by twice m as n, then the values of lambda are given by minus n plus minus root over n square minus omega square. and therefore the general solution of my original differential equation can be obtained as a1 e to the power lambda 1t plus a2 e to the power lambda 2t, where lambda 1 and 2 are given by this equation. Okay. Now, depending on the value of this quantity under the square root sign, I can have three different cases. When n is equal to omega, then what happens? This quantity becomes 0, and therefore both the roots are equal of the roots of the auxiliary equations are equal, and therefore I will have a1 plus a2, which is a new constant, e to the power lambda 1t. Okay, and that condition is called a critically damped system. When n becomes equal to omega, you can see that both the roots are equal, and therefore what I will have ultimately x equal to some constant, say a e to the power minus n t, right? Because I have two terms like this, so a1 plus a2 will be there, which is a new constant a. So it's simply an exponential decaying term, and therefore what will be my what will happen to my variation of vibration, how the vibration will vary with time? It will be just a exponentially decaying function. Okay, so such a quantity can be drawn like this. It will be something, I'm sorry, so I will have a function of, I'm sorry, I'll have an exponentially decaying function, something like this. Okay, and this type of system is called critically damped system. Okay, critically damped system. Critically damped system. On the other hand, if this term is positive, that means n is greater than omega, then I will have two different roots, of course, and they are real roots, and in the case the system is called overdamped system. Overdamped system. All right, system is overdamped. Right. On the other hand, if this quantity is negative, I will have a complex root, two complex roots. This is a real number, this will be an imaginary number because it is negative. So I will have two complex roots, conjugate roots, and such a system is called underdamped system. Okay. Now let us discuss each of them one by one. These three cases. First, let us see the critically damped system when n is equal to omega. So I can write that n square is equal to omega square because n is equal to omega. Now putting the value of n here, we write for a critically damped system the damping coefficient, we call it as a critical damping coefficient, and it is denoted by Cc, right? So I will write Cc by twice m is equal to omega square, which is k by m. So from this I can solve for Cc, and we can see that this Cc is 2 root over km finally. Okay, 2 root over km. And once again we see that this critical damping depends on the value of mass and stiffness of the system. So it is again an inherent system property. Okay, so critical damping of a system is another inherent dynamic property which governs the damping present in the system. So it is again a system property, not an external quantity which depends on some external agent. All right, so this critical damping coefficient, its value you should remember 2 root km, and if I write if I express k in terms of omega or m in terms of omega, then I can also write Cc equal to twice m omega. Okay, because k is omega square m. Okay, so I'll get twice m omega, and that will give me finally, if I express m in terms of k by omega square, then I will get twice k by omega. So Cc can be expressed either in terms of k and m, and because k and m are related to omega, therefore I can express them in terms of m and omega and also k and omega. So this is another important equation we get. All right, this is another important equation we get here. This is important equation. These equations will be useful later on to solve numerical problems, as we will see later on. All right, now once I have this critical damping, I can express the damping present in any system as a ratio of its own critical damping, and in that case, whatever is the damping coefficient, the ratio of that damping coefficient to the critical damping is called damping ratio. It is usually denoted by the Greek letters xi or zeta, and usually it is expressed in terms of percentage. Okay, and if I have this critical damping as 100, if I have this damping ratio as 100%, that means my system is critically damped, because C is equal to Cc in that case, and in that case its motion will be non-oscillatory. It will cross the mean position of rest only for once, and gradually it will try to come back to its original position as we have drawn here. Okay, so this is how a critically damped system will vibrate. Actually it is not a vibration, as you can see. Therefore, except for knowing the value of critical damping, a critically damped system is not of so much interest to us. Okay, it is something like this. Then I have overdamped system. In overdamped system, n is greater than omega, therefore damping coefficient will be higher than critical damping, so C will be greater than Cc. So the roots of the equations both are real and negative, and therefore my vibration will be just like this. It will never cross the mean position of rest. It will be an exponentially decaying function, and it will never cross the mean position of rest. Okay, and that's how a overdamped system will vibrate. Again, it is not really a vibration. So for real structures, we are not much interested in these two types of vibration, critically damped and over damped system, except the fact that the critically damped system is important just to know the critical damping coefficient of the system. And we have already seen that critical damping coefficient of the system is a system property, which is Cc equal to 2 root over Km. I'm just repeating for the sake of remembering, which is equal to 2 m omega n, which is equal to 2 k by omega. So all these three expressions I can use for Cc depending on the known value of the system. Next comes the most important type of vibration from practical point of view, which is underdamped system. In an underdamped system, this n value will be less than omega, and therefore this quantity, which was n square minus omega square originally, that will be negative. So I will write it as n plus minus I root over omega square minus n square, and this omega square minus n square root over will be called as damped natural frequency. So it is denoted by omega d. Okay, so it is the frequency of damped free vibration or damped natural frequency. In that case, what will be my solution of equation of motion? We have got that x was equal to a1 e to the power lambda 1t plus a2 e to the power lambda 2t. When I put the values of lambda 1 and lambda 2 here, this value, then I get these quantities. So if I take e to the power minus nt common, then I get these terms. Okay, so again these terms, e to the power I omega dt and e to the power minus I omega dt, just like a free vibration term, I can express them in terms of sine and cosine functions using Euler equation, and therefore I will get just a simple harmonic motion free vibration, undamped free vibration, but multiplied by this exponentially decayed envelope. So that means how the vibration will take place. The vibration will be something like this. If I draw it here, let me try to draw a straight line, and my vibration will be such that I have an exponentially decaying envelope, and within that my harmonic motion will take place. So gradually the amplitude of vibration will decrease. All right, and that is what happens in all real vibrations, right? Gradually the amplitude of vibration decreases. So that's why underdamped systems are real systems, and we see that it is just similar to my undamped free vibration, but with an exponentially decaying envelope. If I plot them, then I will get a vibration like this. You see, this is my zero axis. It has certain initial displacement, and then it gradually, the amplitude decreases with time. Okay, so that's how, if you join these points, you will get an exponential curve. If I join these points, I'll get an exponential envelope, something like this. Okay, exponentially decaying envelope, which is not shown here, of course. All right, so now let us find out these integration constants from the initial conditions. Let us assume the initial conditions to be initial displacement as x naught and initial velocity as x dot naught. In that case, what I will get? I will get, by differentiating this, I will get value of a as x naught and value of b as this. This you can try yourself. It is pretty easy. You differentiate this as product of two functions, exponential and this. So exponential function will not change during differentiation, obviously. So only thing that will change is this, and we will put t equal to 0 in this term. In that case, my a will be x naught, and if I differentiate this, then I will get b as this much by putting t equal to 0 and velocity as x dot naught. I will get this value. So this will be my solution of equation of motion with initial displacement x naught and initial velocity x dot naught. And omega d is, as I told you, it is root over omega square minus n square. All right. So next, let us find out the value of damped frequency and time period. We have found that omega d is this, and now I am taking omega square common from here, so that outside the root over sign it becomes omega, and then I get 1 minus n by omega whole square, and n by omega whole square, if I put the value of n, c by twice m whole square into omega divided by omega square is multiplied by m by k. So after simplification I will get that this quantity is nothing but c by cc, because cc was 2 root over km, so 4 km is cc square and this is c square, so ultimately I get chi square, and therefore omega d I can write from here, from this equation, as omega into 1 minus chi square, where chi is my damping ratio. Okay, and similarly the damped time period will be, as per definition of time period, twice pi by omega d, and putting the value of omega d from this equation, I get damped time period is this. All right. So this is how we can express the damped time period in terms of damping ratio. Now, what is the physical significance of damping ratio? You see, for most practical structures, the damping ratio lies between 2 to 20%. And if I use damping ratio as 0.2, that is 20%, then omega d is nearly equal to 0.98 omega. That means nearly 100% omega, so almost equal to omega. So for all practical purposes, the damped natural frequency is approximately equal to the undamped natural frequency, and also the damped time period is same as undamped time period. But since we have already seen that in damped vibration the amplitude gradually will decrease, therefore amplitude of vibration will not be same as undamped free vibration. Okay, with every cycle the amplitude of vibration will decrease gradually in case of a underdamped system. Now based on that, we can define another quantity for as a measurement of damping present in a system. You see, from earlier figure, you see the amplitude. Let me draw a straight line here for 0. This is my axis. Okay, and you see that with each cycle of motion, this is one cycle of motion from here to here, from here to here, this is one cycle of motion. Say from here to here, this is a cycle of motion. This is my amplitude here. Let me again draw another straight line, whereas in the next cycle of motion my amplitude is this much. So definitely the amplitude has decreased, right? Now since this peak is touched by this exponentially decaying envelope, and what was my equation of this envelope? It is e to the power minus nt, right? And we have already seen that it is related to xi into omega, right? Let us show you. Sorry. I know that n is xi into omega, right? From this, n by omega is xi, therefore n is xi into omega, and therefore I can write here this as this, I can write as e to the power minus xi omega t. So it is related to the damping ratio xi, and therefore this decrease in amplitude in two consecutive cycles of motion can be related to my damping ratio very easily. And therefore, as another measurement of damping, we define something called logarithmic decrement, which is defined as the natural logarithm of ratio of two consecutive amplitudes in two consecutive cycles. Suppose I have a underdamped system which has consecutive amplitudes as x1, x2, x3, etc. Okay, then this logarithmic decrement delta, it is denoted by delta, is defined as natural logarithm of x1 by x2, and it is also equal to natural logarithm of x2 by x3, and so on. In the earlier figure, we can denote these values as x1 and x2 and x3, etc. Say this height is x1, this height is x2, and this height is, say, x3, and then my delta is defined as natural log of ratio of x1 by x2, and this is also equal to natural log of x2 by x3, and so on. So this is how it is defined. Alright, now let us find another expression for natural logarithm of these two ratios, that is the logarithmic decrement. So what we see is that by definition my logarithmic decrement will be this. Now the equation of motion I can express naturally as r times e to the power minus nt into cosine omega dt minus phi. This r cosine omega t minus phi we have already seen in case of undamped vibration. Now in case of damped vibration, my frequency will be omega d, therefore omega dt term has come. R is already there, and it is just multiplied by this exponential envelope, right? And the value of r from the solution of equation of motion, we can find out that the value of r will be root over this x naught square plus this quantity. All right, and therefore what I can write is now x1, suppose at time t1 the amplitude is x1 and at time t2 amplitude is x2. Let me again go back to the earlier figure. Let me assume that my time here is t1 when amplitude is x1, and time here is t2, and this t2 is what? T2 is t1 plus damped time period, right? This is one cycle of motion. Complete cycle of motion has been over, so t2 is my t1 plus td, is not it? So if I use that in the definition of logarithmic decrement, what I will get? I will get x1 as r e to the power n minus n t1, because when I am considering the amplitude, this quantity must be 1 because it is the peak value of the harmonic term. So this is my 1, therefore r e to the power n minus n t1, and similarly x2 will be r e to the power minus n t1 plus td, right? And therefore when I take ratio of this and then natural logarithm, I will get natural logarithm of e to the power minus n t1 plus divided by e to the power minus n t1 plus td. So I will have e to the power minus n, by using power rule I will have this, and therefore finally this t1 and t1 will be cancelled, and this minus will become plus. So I will have delta equal to natural logarithm of e to the power n td. So natural logarithm of e to the power n td will be the power itself, so n times td, and we already have n equal to j into omega, therefore delta is j omega into td. So this is another important equation. All right, this is another important equation, and similarly this is also another important. I'm sorry. This is another important equation. Okay, so natural the logarithmic decrement can be obtained in terms of damping ratio by using this formula, and since damping ratio for real systems are very small, therefore root over 1 minus j square is nearly equal to 1, therefore sometimes it is also approximated as delta equal to twice pi j. All right, so this is how we can find out another measure of damping, which is logarithmic decrement. It is defined as natural logarithm of amplitudes of two consecutive cycles of motion in a damped free vibration, and that is related to the damping ratio as per this equation 48 here. All right. So this is how we can analyze damped vibration. So to summarize what we have seen that we have three types of systems. One is critically damped, and related to that I have critical damping of a system, and that is a system property which is given by Cc. Then we have already seen the expression, Cc is 2 root km. I'm just repeating for your benefit. Then I have overdamped system, and for the real systems I will have underdamped systems. And in case of underdamped system, I have a damping ratio which is less than 100%, or the damping ratio is less than unity. And we also have another measure of damping present in the system, which is logarithmic decrement, and it is obtained by this equation. Okay, so our next topic, the last topic in this lecture, is combination of springs. Many a times what happens, you remember that suppose if I have to find out say dynamic model of a say two-storied building, okay, or a two-storied frame, what I can have these columns and the floors, and all the masses are lumped at the floor levels, right? This we have already seen, and the vibration will be taking place primarily in horizontal direction, because that is more important for us for engineering purpose. I'll tell why it is so. And then this stiffness of these columns, I have to find out the equivalent stiffness of all the columns to find out the story stiffness in the second story. Similarly, the stiffnesses of all these columns will be used to find out the equivalent stiffness of the first story. So many a times I need to find out the equivalent stiffness of a number of springs, okay, and that is what we will be discussing here, combination of springs and how to find out the equivalent stiffness. It is pretty easy. Now we can have two types of combinations. One is series combination, the other is parallel combinations. Now let us see the springs in series. Okay, I have a figure. This is a figure. I have two springs of stiffness K1 and K2, and it is subjected to the same force, that is weight of the block, that is W. All right. So this type of combination is called series combination, and this type of combination where my two springs are kept parallel, this is called parallel combination. In series combination, what happens? Both the springs carry the same load, whereas in parallel combination, both the springs undergo the same deformation, equal deformation. These are the two key points we should remember. What should we remember? We should remember that here springs carry equal load. Springs carry same load. Whereas in parallel, what happens? Springs undergo equal deformation. Equal deformation. These are the two key points we need to remember to identify whether the springs are in series or in parallel. Now let us find how to get the, let us see how to get the equivalent stiffness of the springs in series. Okay, you see we had, let me draw the figure once again here. It may not look nice, but will be useful to understand. So this is my spring, one spring, this is my another spring. They have different stiffnesses and they are carrying the same load. This is my Q1, This is my K2C and this is my W. Okay, so W must be equal to K1 times the deformation of the spring, first spring, say it is Y1, and deformation of the second spring is say Y2. Then W must be equal to K1 times Y1, and also W must be equal to K2 times Y2 because they are carrying the same load. So Y1 will be given by W by K1 and Y2 will be given by W by K2. Now I will take an equivalent spring so that that equivalent spring undergoes the same amount of deformation. That is, the deformation of the equivalent spring will be sum of this Y1 and Y2. And if my equivalent stiffness is K equivalent, KEQ, then this W must be equal to the equivalent stiffness times the deformation of the equivalent spring, which is Y1 plus Y2. So therefore Y1 plus Y2 is W by K equivalent. Okay, now let us put the value of Y1 and Y2 here from the earlier equations. Then what I will get? I will get pretty easily from here. I will get W by K1 plus W by K2 will be equal to W by K equivalent, and therefore my 1 upon K equivalent will be equal to sum of the reciprocals, 1 upon K1 plus 1 upon K2 and so on. If I have 3 springs, 1 upon K3 will come and so on. So this is similar to parallel combination of resistors from physics or electrical engineering. You must have learned this, that when the resistors are connected in parallel, the equivalent resistance is given by this formula, similar formula. So in springs in series, I have the same formula. 1 upon K equivalent is equal to 1 upon K1 plus 1 upon K2 plus 1 upon K3 and so on. Okay, sorry, it should be K2 here. Okay, and so on. So this is how I can get the equivalent stiffness of springs in series. Similarly, let us consider now the equivalent stiffness of parallel springs. So in parallel spring, what is happening? The load is shared, so and displacement is equal. So if the displacement is y, then K1 times y plus K2 times y will be equal to W, right? And that is what we are writing here. And the equivalent spring will also undergo the same deformation. So y times K1 plus K2 is W, and equivalent spring will also undergo the same deformation. So K equivalent into y equal to W. So by equating these two, since right hand side of these two equations are equal, therefore left hand sides are equal. So y times K1 plus K2 is equal to y times K equivalent. So therefore K equivalent is K1 plus K2. And this is the case of resistances connected in series. So in the spring case is just opposite to combination of resistance case. Okay, so therefore I will have, in case of parallel springs, to get the equivalent spring constant, I can simply add their individual spring constants. And in case of series combination, I have to add the reciprocals. Okay, that is the only difference. So this is how equivalent springs are obtained. Now in the next class, we will take up a few problems of undamped and damped free vibrations. So stay tuned for that class. Thank you very much.